Morning, everybody. Today we're going to be talking about looking at Newton's laws of motion, and in particular the second law, although there's going to be some stuff in here about all three. The second one we tend to focus on more when we're doing math problems because it's got math built right into it. And just before we get started, I'm going to flip over on the back of my paper here, and I'm just going to make a couple quick notes, and you're welcome to jot these down too. Just talking about Newton's three laws. The first law is the one where I break my pencil lead right off the bat. The first law is the law of inertia. Okay, and that simply says that something inherent to all matter is that it resists acceleration. Or in other words, you often hear this one referred to as an object in motion stays in motion, or an object at rest stays at rest. The other side of that, though, is that if it's acted on by an unbalanced force, which is the kind that causes acceleration, then it will, of course, accelerate. But it will resist that acceleration. And the more matter you have, the more it resists it. Okay? If I have a toy car versus a real car, and I go to push both of those, the toy car is going to have less inertia because it has less mass, so it's going to be easier for me to overcome its inertia and actually get it moving. Whereas if I try and push a real car, I have to use quite a bit more force to overcome that inertia and get it going in the first place. Newton's second law, like I said, is the only one where there's math built into it, and it's the formula F equals M times A. Okay? Or in other words, force equals mass times acceleration. And there's a number of different ways that you can rewrite this formula. We can make a magic triangle out of it if we want to, which I sometimes find handy, where we've got F over M and A, kind of like that. So if I want to find force, I cover up F, it's M times A. If I want to find acceleration, then it's force divided by mass, and if I want to find mass, it's force divided by acceleration. Something that's important to keep in mind, especially for some of the problems that we're going to see here, you remember that mass and weight are not the same thing. Now, let's talk about what weight actually is, and this is a really cool way to think about it. Weight is actually a force. Okay? You're saying, what force is it? Well, it's the force of attraction between an object and the planet or moon or whatever that it happens to be standing on. Okay? It's a measure of the force of gravity. So, if we're talking about anything having to do with weight, then its acceleration, if you're on planet Earth, is going to be 9.8 meters per second squared. Okay, you already know that one. That's true for objects on Earth or in free fall around Earth. It's important to keep that in mind. So, if I say that I weigh way too much, but let's just, say that I weigh 220 pounds, what that measures is the force of attraction between the Earth and my mass. If I was to change my weight from pounds into newtons, okay, which is a thing you can do because newtons, I think I probably ought to write that down, force is measured in newtons, then I could use acceleration here to calculate what my mass actually is. I just take my weight in newtons divided by 9.8, and that would give me my mass in kilograms. Okay, so I guess I should probably also put that down. Mass is in kilograms. Acceleration is in meters per second squared. Okay. Third one, just a very quick mention. Newton's third law is the one you always hear about as the action-reaction law. That's not entirely accurate because action-reaction implies that one happens and then the other happens, when in reality, they're happening at the same time. If I apply a force to an object, at the same time that object is applying an equal force to me in the opposite direction. So I like to think about 3 as the equal opposite forces law. Okay, you sometimes hear about it as the force pairs law, because forces of an object acting on another object always happen in pairs. The question on the checkpoint about the guy jumping off of the floor in the basketball game, he's applying a force downward with the muscles of his legs. He applies a force to the floor. That floor applies a force to him, and that's what actually pushes him up in the air, which is a really weird way to think about it, but that's the physics behind it. That's what's actually happening. Okay, when you jump, you're jumping because the floor is pushing you up, because you pushed on it first, or at the same time. So that's all the notes. Let's go take a look at some of these practice problems and shoot through a few. Okay, so some of these are actually going to involve math. A lot of them are just going to be thought problems. The first one, if you were in a spaceship and launched a pumpkin into frictionless space, how much force would have to be exerted on the pumpkin to keep it going? All right, if anybody thinks you know that one, type it up in the chat. It's a lot easier than you think it is. Nobody's typing anything. And everybody's either, headed off to Allsup's to grab a Tulsup, or, you're doing nose goes and I just can't see it. I don't know what's going on here. It would be none. That is correct. Okay, the key right there is how much force would have to be exerted to keep it going. Well, if you're in frictionless space, there's no force acting on it. And so according to first law, an object in motion is going to stay in motion unless a force acts on it. Its inertia is going to keep it going. So the answer is 0. 0 force, 0 newtons. Okay, now number 2 is fun. An elephant and a mouse would both have 0 weight in gravity-free space. If they were moving toward you at the same speed, would they bump into you with the same effect? Yes or no? And explain. Okay, what do y'all think? What instinctively do you think? If you're out in space and a space elephant comes floating toward you, or a space mouse comes floating toward you, and they hit you, is there going to be a difference in the effect they have on you? Oh, I like that. That's a nice, safe answer. Maybe, even if there's 0 weight, they have different masses still. That's the key right there. Because, yeah, there is no weight, but they are coming to you with different masses. And so if you get hit by a flying space elephant, it's got quite a bit more mass, and so its larger mass is going to hit you with more force. So therefore, it's going to cause greater acceleration in you, right? Whereas if you hit me with a space mouse, the space mouse is going to hit me. It's going to impart some force, and yes, I'm going to accelerate and float a little bit, but nowhere near as much as if the elephant hit me. There's this series of books that I read called The Expanse, and they talk about how they're out in zero gravity and they're harvesting ice and stuff from like a comet or an asteroid, and they're loading it, these massive, like bigger than a building, chunks of this stuff into the spacecraft, basically just kind of by pushing on it. But you have to be really careful because even though those are moving really, really slow, if you get stuck between one of those and the wall, it can still crush you to death. It can still apply enough force to you to kill you, or lop off an arm or something. Because even though there's no weight, there is still mass. And where there's mass in motion, there is force. Okay, so would they bump into the same effect? I'm going to say no, and I'm going to explain more mass would mean more force, and therefore more acceleration on me. John King writes, you stole. No, I don't. Give me just a cotton picking minute. They're in the bathroom. They're in the bathroom, comma, dingus, period. Look on your shelf, period. I didn't move them, period. Okay. Sorry about that. So let's see. Okay. What's the weight of 2 kilograms of Jello, and what is the weight of 2 kilograms of lead? We're going to do a little bit of math on this one, but before we do any math on this one, what's your instinct regarding this? Do you think that they will have the same weight, or do you think they will have different weights? No, that's okay. Yeah, that is what I'm asking. Same weight or different weight? Assuming that we're weighing them both on Earth. Okay, Emma says same, Tatum says same. I would agree. So all we need to do is figure out, yeah, 2 kilograms is 2 kilograms. You've got the same mass. So let me get some scratch paper. Oh, I'll just do it on the back of this other one here. So if force equals mass times acceleration, let me make myself a little triangle. Okay, if I'm trying to find the weight, I'm trying to find the force. Okay, so it's just going to be mass times my acceleration. So that's just going to be 2 kilograms times 9.8 meters per second squared. So 2 times 9.8 would be 19.6. Now, let's talk about units for that, because this unit, if we're doing kilograms times meters per second squared, then my unit is going to be kilogram meters per second squared. You know another really fun thing? A kilogram meter per second squared is the same as a Newton. Okay? It's a derived unit, so you can just say 19.6 newtons. Easy peasy. Okay? Okay, now I'm glad this is coming up because we did have some questions about net forces. Forces of 10 newtons and 15 newtons pushed to the right on an object. What is the net force on an object? Okay? So net force simply means total force. And I'm glad that this came up. I think Tatum had a question about this. So net force is the sum of all forces. You have to remember that positive and negative have to do with direction. So this right here, this is the Greek letter sigma. It means the sum of something. So anytime you see a sigma, that's what that means from here on out. So the sum of all forces, so if we're looking, we've got 10 newtons and 15 newtons pushing to the right. They're pushing in the same direction. So I wouldn't have to make either one of those negative. So 10 plus 15 just means that the net force is going to be 25 newtons to the right. Okay. Now, you tell me number 5. A force of 15 newtons pushes an object to the right, and a force of 10 newtons pushes on the object to the left. So what would the net force be on that object? What do you think? I need a number and I need a direction. Y'all out there still? I think I've lost you. I'm getting 5 newtons to the right. Yes, 5 newtons to the right is correct. If you look at it like a force diagram, if I've got 15 newtons, pushes it to the right, so there's my 15. Here's my 10 to the left. Then, yes, you just do 15, which would be your positive, 10 would be your negative. If you decide to do it, you could also say 10 is positive and 15 is negative. But you make one of those equal to the right, and so that plus negative that is going to be 5 that direction, 5 newtons. Okay, I've been talking for 16 minutes. So 6 and 7 are both weight and mass problems. I think I'm going to leave 6 and 7 for y'all to take care of on your own. Let's look at problem number 8, because this is a really fun thought problem. If an elephant's chasing you, its enormous mass would be very threatening. But if you zigzag, the elephant's mass would be to your advantage. Oh, Lula Nolan has a question. Lula, unmute yourself. Which question?
So for like when we write the 5 newtons to the right, can we just write like 5 and then like an arrow?
Yes, because I'm not that picky. That's fine. Okay, so getting back to the elephant. Well, if you zigzagged, why would the elephant's mass be to your advantage? This is not math, this is more concept. When you're zigzagging, you are changing direction. Changing direction is a form of acceleration, correct? So if I change my direction, if I accelerate, I can do so relatively easy because I have very little mass. Meaning that I have, well, part of it is greater masses have slower acceleration rates. But also keep in mind the elephant's going to have a lot more force behind its muscles than I will, so that'll kind of overcome that. But in order for me to accelerate, I have to overcome my own inertia. So does the elephant. So anytime it changes direction, it's got quite a bit more inertia that it has to overcome in order to accelerate. It's kind of like hitting the brakes if you're driving a little compact car versus hitting the brakes if you're driving a bus. It's going to take a lot more force applied in order to overcome that. And then it's going to take a lot more force to get it moving again in a different direction. Okay, so if I wanted to just phrase that in a few words, I might say that an elephant has more inertia to overcome. Ouch. We can do number 9 together. Number 9 has got some interesting bits and pieces to it. It's some multi-part thinking. So if a woman weighs 475 newtons on Earth, but 1,260 newtons on Jupiter, what's the acceleration of gravity on Jupiter? So let's talk about what we know, and I'm going to make myself just a little chart here, Earth and Jupiter. So we know that the force on Earth is 475 newtons. We know the force on Jupiter is 1,260 260 newtons. Which means that the acceleration on Jupiter is going to be something different, right? And that's what we're trying to find. So what's the only other thing we're leaving out of this? Mass, exactly. The woman has mass, correct? Is her mass going to be the same, or is it going to change if she goes somewhere else, say Jupiter? Now my weight will change if I go different places because it's different things accelerating me. But the amount of stuff that I'm made of, my mass, will stay the same. That's exactly right. Okay, so what we need to do is we need to find her mass on Earth and then take that and apply it to the force on Jupiter to find its acceleration. So a little triangle, force equals mass times acceleration. So if I want to find her mass, I'm going to do force divided by acceleration over here. So 4.75 divided by 9.8. I'm not going to try and do that in my head. That we can see it divided by 9.8. So she has a mass of did I do something wrong? Oh, 475, you dingleberry. I was like, this lady is really tiny. She's like a midget. Okay, no, actually that's 475 divided by 9.8. Dingleberry. So she has a mass of 48.47 kilograms, okay? That's going to be the same as her mass over on Jupiter. So to find her acceleration on Jupiter, cover up the A, it's going to be force divided by mass. So this 1260 divided by the number I just got, so let me do that. I'm just going to do 1260 divided by answer. Tells me that her acceleration is 25.995. So I could even say 26.00 meters per second squared. Okay. Ooh, that is more than twice the acceleration of gravity on Earth. So yeah, no wonder she feels so heavy. So I guess I could put that down on 9. I'm going to say 26.00 meters per second squared. I've been talking for 23 minutes now. Now there's quite a few more problems. I am not expecting y'all. Falling on Jupiter would be very painful. Yeah. Now we're learning in astronomy a really interesting thing about Jupiter, bunny trail. Since it is mostly gases, the upper parts of Jupiter are not very dense, and so you would basically fall through the quote-unquote surface of Jupiter. But there's so much gravity as you get into Jupiter that the core of Jupiter actually has layers that are liquid hydrogen and then solid metallic hydrogen down at the very, very core. So, I mean, even if you were able to survive the fall, which you wouldn't, because the pressure from all of that would kill you, the sheer forces of gravity would kind of crush you into people jello well before you hit the ground. Okay, so yeah, not a fun place to be. I've been talking for quite a while now, and I'm tired of hearing myself talk. I do not expect you to work all of these problems on your own. In fact, I think what we're going to do is I'm going to let you work on a few more on this front page before we get back together again. But I think we're going to save the second page right here. I don't know if we're going to do it some more this week or if we're going to get into something else this week. I think that I had planned something else. But anyway, hold off You can go ahead and do number 6 and 7 on your own. And okay, I like number 10. I'll let you do number 10 on your own. 11 and 12 are not math so much as they are just reasoning and thinking about things. And I'm going to let you do 13. So if you can do 6, 7, 10, 11, 12, and 13 before we get together again, when we get together, we'll check and see how you did on those. And I think that's going to be it for today. So thanks for joining me. Don't bug out of the thing just yet, because I'd still like to get a picture just to prove that you're all here. But I'm going to go ahead and end the recording.